This is Advanced Higher Chemistry. We are talking about Unit 1, and in Unit 1 we're looking at inorganic chemistry. And the topic that we're looking at now is atomic orbitals, electron configurations and periodic table. And this lesson we're going to focus on atomic orbitals and quantum numbers. So firstly, we'll flash back and talk about electron shells, or energy levels as they're otherwise known. Absorption and emission spectroscopy proved the existence of discrete quantized energy levels. However, these energy levels are a bit more complicated than you have previously been taught. Each energy level can be divided into sublevels, which we call orbitals, and different types of orbitals have different shapes. So the image you have in your mind probably of a nucleus surrounded by these spheres, which represent the energy levels, is a bit more complicated, and some of the energy levels are definitely not spherical. Now, we said that these energy levels are subdivided into things called orbitals, and an orbital is a volume of space in which there is a greater than 90% probability of finding an electron. The reason why we cannot say with 100% certainty that you will find an electron inside an orbital is because electrons, like photons, behave like waves and particles. And so their wave-like behavior means it's very difficult to specifically locate them, which is why in orbital we can only say there is a greater than 90% probability of finding an electron. Now, here we have an illustration of all the types of orbital that are known for atoms. And you can see they're all different shapes. For advanced higher, you'll only really focus on the red, yellow and blue ones, not the green ones. Those green ones, in fact, aren't properly explored until more than halfway through a university chemistry course. So you don't need to worry about them, but just have a faint knowledge that they exist. So we're going to talk about the different types of orbitals in turn. We're going to start with the red ones, which are called s orbitals. Then we'll talk about the yellow ones, which are called p orbitals. And finally, we'll talk about the blue ones, which are called d orbitals. Now, these letters might seem like they're a bit random, S, P, D, and F, but these letters come from the form that the lines in the emission and absorption spectra look like for these types of orbitals. So the s orbitals are called s orbitals because the spectral lines that they produce are sharp. You then get a bit more detail from the p orbitals because those lines are called the principal lines. With the d orbitals, the lines are a bit harder to see and they are called the diffuse lines. And F stands for fundamental, and they are probably the most hard to see, but are the best at actually helping you to distinguish an atom of one element from another. So we'll focus on the s orbitals. The s orbitals are the spherical ones, and they are the ones that are probably what you thought energy levels looked like. The bigger the energy level, the bigger the sphere. So if you are an orbital in the first energy level, you'll be a certain size. If you're in the second energy level, you'll be a bit bigger. And they're described as being the 1s, the 2s, the 3s, depending on which period of the periodic table they're in. So 1s for the first period, 2s for the second period, etc. The p orbitals are peanut shaped or dumbbell shaped. The two main descriptions used for them. There are always 3 p orbitals, and if you look at the diagram on the right hand side, they point in different directions. If we draw a set of axes using x, y and z as the labels, one points along the x-axis, one points along the y-axis, and one points along the z-axis. You don't need to worry about those x, y and z labels. You just need to know that there are 3 of them and they all point in different directions. Next we have the d orbitals. Now d orbitals are not all the same shape. you can see from the diagram on the right hand side that 4 of them are cross-shaped or X-shaped, but there is one which is called the DZ squared, which looks like a p orbital except it's got a ring around the center. And that's what makes it different. So 4 of them are cross-shaped and one of them is a peanut with a ring around the middle. The d orbitals we'll come back to whenever you look at transition metals, because d orbitals are where the outermost electrons on transition metals are found. Now orbitals, there are different orbitals within the same energy level, and an energy level can contain multiple types of orbitals. Each orbital can only hold 2 electrons maximum. Part of the reason for that is that electrons have a negative charge, and if you try and put 2 negative things close together inside an area of space, they're going to repel. The more negative things you try to put together, the more they will repel one another. So when an orbital is able to tolerate 2 negative things inside it without it completely being destroyed by the repulsion. Each electron possesses a fixed amount of energy. So because it's in a particular energy shell, it has a fixed amount of energy called a quanta. And we can describe the position of the electron and its energy in terms of things called quantum numbers. So the quantum numbers are used to describe each electron in an atom. Now this is really important that you remember the quantum numbers describe each electron. They're not used to describe orbitals, they're used to describe electrons inside orbitals. And we've already gone over a comparison of orbitals. If you're watching this presentation live, you can click on that link and it'll take you to a website that allows you to look in 3 dimensions at the orbitals. So now what we're going to look at are the quantum numbers, and there are 4 quantum numbers. We start with the principal quantum number, then we have something called the angular momentum quantum number, the magnetic quantum number, and the spin magnetic quantum number, which is sometimes just called the spin quantum number. So the principal quantum number has a symbol of n. So remember, whenever we were looking at absorption and emission spectra, we were talking about n equals 1, n equals 2 for the different energy levels. That's what this n is. And it indicates the main energy level, or the size of the orbital. So if an electron is in n equals 1, that means it's in an orbital that we would think of for the first period. If it's in n equals 2, it's in a bigger one, n equals 3, even bigger. The angular momentum quantum number has a symbol of L, and L can have lots of different values. And the values of L start at 0 and they go the whole way up to n minus 1. So if n was 1, there would only be one possible value of L, which would be 0. If n was 3, you could have an angular momentum of 0, an angular momentum of 1, or an angular momentum of 2. Each of the values of L corresponds to a different type of orbital. So if an electron has a quantum number, an angular momentum quantum number of 0, that means it's in an s orbital, of 1, a p orbital, of 2, a d orbital, and of 3, an f orbital. Then the next level of describing an electron is the magnetic quantum number, and it has a value of m with a wee small l beside it. And the magnetic quantum number, again, there is a range of these depending on what the angular momentum was, because your magnetic quantum number, can go from minus L to plus L. So for example, if you have an angular momentum of 1, meaning you're a p orbital, the values that are possible for the magnetic quantum number are minus 1, 0, and plus 1. So you'll notice for p orbitals there are 3 magnetic quantum numbers, and that corresponds to the 3 types of p orbital. And so this magnetic quantum number basically tells you about the orientation of the orbital, which direction it faces. For d orbitals, which have an angular momentum of 2, the magnetic quantum number can be -2, -1, 0, +1, or +2. There are 5, and that tells you which of the 5 different possible d orbitals that your electron is in. And finally, we have the spin magnetic quantum number, sometimes just called the spin quantum number, which is an m with a small s. This only has 2 possible values, +0.5 or -0.5. And this describes what we call the spin of the electrons. So in order for electrons that are both negatively charged, in order to fit inside the same space and not repel one another, they need to spin in opposite directions. And that's what this +0.5 and -0.5 represent. +0.5 we can imagine as being a clockwise rotation or a clockwise spin, -0.5 being an anti-clockwise spin. And so if electrons are in the same orbital, the only thing that will tell them apart is one will have a +0.5 spin, the other one will have a -0.5 spin. The most common exam questions are related to the angular momentum quantum number, where you would be asked to relate the angular momentum to whether it is an s, a p, a d, or an f orbital. And the next most common one is if they give you 4 quantum numbers to describe an electron, and you would be asked to write the 4 quantum numbers for an electron that is paired with that one, in which case all you need to do is write the first 3 quantum numbers exactly the same and change the sign of the spin quantum number. So sort of summarizing that, if the principal quantum number n is 2, then the angular momentum could be 0, 1, or 2, which means an electron could be in an s, p, or d orbital. From that, if the angular momentum quantum number is is 1, it means the magnetic quantum number could be -1, 0, or +1, and that indicates the 3 possible p orbitals, px, py, or pz. If, however, the angular momentum quantum number L is 0, it means that the magnetic quantum number could only be 0. And that's because where we have s orbitals, there's only one type of s orbital for every energy level. So that has been an introduction to atomic orbitals and quantum numbers, which are used to define the electrons within orbitals. We will be continuing looking at sp and d notation and the periodic table in the next lesson.